So another thing that I wanted to share with you in terms of this week's screencast is I got to thinking about drift velocity versus current. And I tried to, I guess I was a little confused there. I had the understanding that drift velocity of charge was much slower than current, it seems. But anyway, so uh, drift velocity seems to be just this kind of, you know, motion of these charges, and then there is a net movement of the charges through a certain area. Um, and it's obviously not the same as current. And so I guess I got to thinking about that. And, this is a neat diagram that kind of really helps me put my head around it and how um, the current is the total amount of charge, is the rate of charge flow, and drift velocity is used to determine the total amount of charge. And so this equation really helped me. I'm not sure if we're going to be using this equation here, where current is equal to the number of charges times the charge of an individual charge times the cross-sectional area times the drift velocity. And so this is a pretty elegant derivation, I guess, of that using sort of a couple other equations. And so I thought that was useful. And so I guess I mention one more thing is that in terms of the lab, yeah, like I was ending the last screencast, I was wondering, if this lab, this wouldn't be necessarily a good paradigm lab to use, I don't believe, to determine what's happening in the wires. Maybe one of CASA labs, but once you get into current flow through circuits, you got to be careful in terms of just making it using analogies rather than trying to get at the exact mechanisms for why charge flows. I like the attempt to try to develop the idea that, okay, well, you're going to find potential differences, which will result in electric fields, since electric field is equal to potential difference divided by displacement. And so, it's great. And so once you have an electric field, then you will get charge flow. And so that was very nice. I thought a couple of the graphs, I guess the voltage spikes in discharging a capacitor, but I'm wondering why, for example, for 5B, the voltage only spikes to something like 1.4 volts when you first connect the circuit. And so that's the discharging of the capacitor. And I guess it doesn't go instantly to 4.5 volt potential difference, which is what we should see between the terminals, but it only goes to 1.4 volt potential difference. And so I guess that's interesting, and that requires a little more thinking, and suggests that the charge flow happens gradually rather than sort of all at once, and that sets up electric fields of different strengths as time goes on. So anyway, that's it's a rich lab, and causes a lot of thinking. But anyway, like I said earlier, that this lab needs to be prefaced, I think, by some suggestion to the students that there is you know, there are these electric fields set up that causes charge flow.